Okay, so hello, how are you all doing? Super good. So we're down to 7 people here. Oh, look at that. What's that sound? Okay, so we're gonna finish section 4.4 today, and we'll start 4.5. Yeah, kinda, yeah. So we're already in there. We just have a few little things to cover. So plan for today. We will finish 4.4 and start 4.5. So your quiz, what is it, quiz 5? I don't know if you got my email. Yeah, so it's not due till Friday because we still need section 4.4 because there are 2 homework assignments. One of them you can already complete. The other one you'll be able to complete after today. So quiz 5 due by the end of Friday, which would be 18th, something like that. Is that close enough? 18th, is it? Yeah, 18th. And quiz 6, as of right now, also been pushed to Wednesday, due by the end of Wednesday, and that would be a week from Wednesday, so 23rd maybe? And there's only one homework assignment before quiz 6. So there only quiz 6 only covers 2 sections, covers section 4.5 and 4.6. So there's only one homework before that in order to open that quiz. Okay, so here's the little plan. So I want to do a few examples based on what we did last week. See how much we remember. So here's an example. I want us to find a polynomial of 5th degree. So it has with -2, -1/2 as a 0 of multiplicity 2. It also has 0 as a 0 of multiplicity 1. And it also has 1 as a 0 of multiplicity 2. So basically we have the list of zeros and the multiplicity. So I want to find a polynomial function of degree 5 that satisfies these 3 conditions. Okay? So let's try that. So if -1/2 is one of the zeros, what is the factor? X plus 1/2, right? And squared because of the multiplicity 2. So I can say that much. Okay? Now, if 0 is a 0, what has to be a factor? Just x, right? X minus 0, just x. And if 1 is a 0, what has to be a factor? So x minus 1. But multiplicity is 2, so squared. Okay? Right. So yeah, the multiplicity basically gives you the exponent, and the sum of all multiplicity should give you the total degree of the polynomial. Well, but this x produces 0 as one of the zeros, right? Because it has to have something. It's, remember, if, yeah, so when you set it to 0, you get x equals 0. Now, another way to write this, x plus 1/2 can be rewritten as 2x plus 1. It still gives you the same negative 1/2 as a 0. Do you agree with that? So you can do that. Well, not necessarily, but it's just an option. Yeah. But regardless, even if we don't do that, it'll just be easier to expand everything if you write it like that. Because remember, it's just a polynomial, so it doesn't have to be. Now if we expand that, 4x plus 1 squared will give us 4x squared plus 4x plus 1 times x times x minus 1 squared gives us x squared minus 2x plus 1. That's right. That's just doing a squared minus 2ab plus b squared. Okay? No, that's all right. So then throw in the x. Let's say if we distribute the x through one of those parentheses, we'll get 4x cubed plus 4x squared plus x, and then x squared minus 2x plus 1. Yeah, either first one or the second one, that doesn't matter. And then we'll do a big long FOIL, and that will give us the actual polynomial. So 4x cubed times x squared is 4x to the 5th. 4x cubed times 4x negative 4x cubed times negative 2x is negative 8x to the 4th, and then plus 4x cubed. Is that okay? I'm just distributing. So 4x squared times x squared is 4x to the 4th, then minus 8x cubed, then plus 4x squared. And finally, when you multiply everything by x, you'll get x cubed minus 2x squared, and then plus x. Just do the FOIL. Okay, nothing fancy. So combine like terms, you get 4x to the 5th. And then what do we have for the power 4? It is negative 8 plus 4. So negative 4x to the 4th. Then for the cubics, we have positive 4, negative 8, and a positive 1. So what is that going to give you? Negative 3. So negative 3x cubed. And then you have 4x squared minus 2x squared, so that's 2x squared. And then plus x. Okay? So that will be, yeah, it's one of them. Okay, there are infinitely many of those answers. If I multiply this whole thing by 17, it wouldn't change the fact that it will have negative 1/2 as a 0 of multiplicity 2, 0 of multiplicity 1, and what was it? Positive 1 of multiplicity 2. You can always multiply by any constant, it won't change the zeros. Okay? Just remember, if you multiply by constant, it just stretches the graph or contracts the graph, but that does not change the x-intercept. So this is one of the answers. And we kind of cheated here, made our life a little bit easier. Instead of messing with a fraction, we just rewrote it as 2x plus 1. We just kind of thought of it, well, what else produces negative 1/2? Oh, well, that's just because I'm not paying attention to details. Oh, no, 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 no. Yeah. We usually use P's for polynomials, but start with an F. So anyways, that's about it. Does that make sense? Okay. Let's try another one. Yeah, we'll do that. Let me just do very similar problems. So still find a polynomial of degree 5 that has the following zeros. And the zeros are 3/4, negative square root of 3, and 2i. Okay? Nothing is mentioned about multiplicities. Okay, so these are the three zeros, and the degree of the polynomial is 5. Okay? Well, we have to be, yes, we do have to decide something, but we have to be a little careful. And this is what we talked about last week. If your polynomial has a complex zero with imaginary part, so what else has to be a zero of your polynomial? The conjugate. So if 2y is a zero, then automatically negative 2y is also a zero. Okay? So automatically negative 2y is given to us for free. Okay? Now, if I said find the polynomial with rational coefficients, then also the irrational numbers have to come in conjugate pairs. So if your polynomial has rational coefficients, then if negative square root of 3 is a zero, then its conjugate also has to be a zero. So positive square root of 3 has to be a zero of that polynomial. Otherwise, you will end up with the square roots in the coefficients. Okay? All right, well, now we have all 5 zeros. So therefore, we have all 5 factors. So our function is x minus 3/4, x minus square root of 3, x plus square root of 3, and then x minus 2i, x plus 2i. Yeah, so, well, if you're in doubt, because remember, if you set it equal to 0, you're going to have negative x minus 3/4 equals 0, right? Well, what is the denominator? 4. If you multiply both sides by 4, you'll get 4x minus 3 equals 0. So 4x minus 3 can be one of those factors. It still produces positive 3/4. Right? So this is just easier to do the FOIL. So this is not the same as the original, because there's, multiplying by 4 all of a sudden, but it will still give us one of the answers. So I can actually do this. I can say this is 4x minus 3. Now, I can multiply these two parentheses really fast using a difference of squares formula. So this is x squared minus the square root of 3 squared. So that will get rid of the radicals. And I can multiply the last two parentheses really fast using the same formula, x squared minus 2i squared. Or I can use the product of complex conjugates formula, but anyways. So this takes us to 4x minus 3, x squared minus 3, and then x squared. What is 2i squared? What is that going to equal to? well, negative 4, right? It's negative of negative 4, like that. Minus in between, and then I squared is a negative, so really that becomes x squared plus 4. So x squared plus 4 goes here. Right, the square root goes away. Well, yeah, so the 9 gives you negative, so the sign changes to a positive. Yeah, that's right. Is that okay? Well, now the rest is just foiling this out. Okay, I don't know if I want to keep going. Just do the FOIL. Okay? All right, so that was fun. Now let's do those problems that we were doing at the end of last week. So I'm going to give you a polynomial.
What was the last term on that one?
Yeah, x squared plus 4. Yeah. So we'll start with the polynomial x cubed minus 6x squared plus 13x minus 20. And I want to find all zeros of that function. Okay? So, and I'm going to give you a start, and that came up last week. What if I don't give you a place to start with? Remember how I was giving, here's a function, here are the few numbers you might want to look at first, and then we started doing the synthetic division. We were checking whether the remainder comes out to be 0. Remember that? And you were very happy that I was giving you a place to start. Because if I don't give you a place to start, you're kind of stuck right now. Because if you're just going to start guessing which number might work, how many numbers can you choose from? And all of them, right? Any number can work potentially, so that's really not a good way to do those problems. So I'm going to give you a hint on this one. So let's test x equals 4 first. Okay? So that means we're going to run through the synthetic division. So we're going to put 4 on the outside, and on the inside we're going to put all the coefficients, and we have to be very careful not to skip any powers. Remember, if you're missing a power, we'll have to put 0. But everything is there, right? Cubic, quadratic, first power. So 1, negative 6, 13, negative 20. So if we do the division, 1 falls through. 1 times 4 is 4, so 4 goes here. Then we add negative 6 plus 4 gives us negative 2. Then you multiply again. So what do you get? Negative 8. We add the 2, we get positive 5. 4 times 5 is 20. So yes, it came out to be 0. So 4 works. X equals 4 is one of those zeros. Well, I know, and that will be the big topic of today. But everything is built on last week right now. We haven't done anything new yet. But the key here is to realize that here's the quotient, and the quotient is a quadratic, and we can always solve quadratics regardless of what they look like. Because right now my polynomial is x minus 4 times this quadratic, which is x squared minus 2x plus 5. That's how we read the quotient. So I can always set that quadratic to 0 and find the rest of the 0. So if I do that, x squared minus 2x plus 5, set it equal to 0, I cannot factor that, so I'll probably use the quadratic formula. So using the quadratic formula on that, so negative b gives me positive 2 plus or minus the square root of b squared, so that's 4, minus 4ac over 2a, right? Using the quadratic formula. So this is 2 plus or minus the square root. Looks like negative 16, is it? 4 minus 20 over 2. So this is 2 plus or minus 4i over 2. So that's 1 plus or minus 2i. Right?
So that's a 0
So those two are the zeros.
plus x.
Plus x equals 4, right? So x equals 4 is one of the zeros, and those two are as well. Okay, so here are my 3 zeros. And again, my truly complex zeros came with a conjugate friend. So those always come in conjugate pairs. So the zeros are x equals 4 and x equals 1 plus or minus 2i. Okay? Actually, this means that no matter what our polynomial is, we can always factor it into the product of linear factors. We can always go linear. Because right now, our polynomial is x minus 4, and then x minus whatever this 0 was, x minus whatever the other 0 was. So this is the product of linear factors right now. So we can always break down, no matter what the polynomial is, it can be written as a product of linear factors, no matter what it is. Okay? You can always go all the way down to linear if you allow complex numbers like that. This is actually called the fundamental theorem of algebra, that any polynomial can be broken down into the product of linear factors. Okay? I'm not going to write that theorem down. It's not that. It sounds very important, but, well, you mean you need to understand what I just said. Okay. Is that all right? No, we're done. I mean, this is the problem was find the zero, so we actually finished right here. That was the end of it. I was just showing you that this means that I can do this, the linear factors. So I can always go down to the linear factors. Now, here's another one. You have a formula that tells you how to factor x cubed minus 8. Remember that? That was the formula that I told you, like if you need it, I'll give it to you, the difference of cubes formula, so forth, that students usually forget that it exists. But let's say starting today, I require you to be able to factor this polynomial regardless of whether you know formula or not. And the way we can do that, can you guess one of the zeros of this polynomial? 2, right? If x equals 2, that will be the 0, 1 of the polynomial. So if I divide this, if I run 2 through that polynomial, I'll be able to factor that. Because look, if I put 2 on the outside, what are the coefficients? Well, 1, 0, 0, negative 8. So if I run the synthetic division through that, 1 comes down, 1 times 2 is 2. Add the two numbers, you get 2. Multiply again, you get 4. Add the two numbers, you get 4. Multiply again, you get 8. Add, you get 0. So this right here, x minus 2 is one of the factors, and whatever's left is that quadratic. So really, I just came up with the difference of cubes formula without really using it. We can still do that type of factoring by running synthetic division if you know that something is already a 0. Okay?
If you have it in that form, as long then it would always
Yeah. You can always find that real 0. Real 0 is easy one to find. Yeah, and even if you set it equal to 0 and you solve for x, you have to cube root it till get you 2. But it'll give you that one real root. It doesn't give you the imaginary ones. Yeah, you can do with any, yeah, the sums of difference of cubes. If you know the real one, you do the synthetic division, and you'll get the quadratic that can always be solved. We can always solve quadratics. Okay? All right. Well, you set it equal to 0, and then you use the quadratic formula. And we've done this in class before, but we did the factoring differently. We used the actual formula to factor. Now we just use the synthetic division trick to get our factors out of it. Okay, and this is the benefit of using the synthetic division, because it reduces the degree of your polynomial. The quotient always of a lesser degree is your starting polynomial. Okay? All right. So what we just said, that any polynomial can be factored into a product of linear factors. So factored into a product So this means if this is my polynomial, I can factor this like that. So some linear factors, so bx minus c with some subscripts. I don't know if you want to be writing this down. I want to talk about something new and so forth. Okay? Now think about foiling the right-hand side. If you foil the right-hand side, at some point you'll multiply C1 by C2 by C3 by C4. At some point you'll multiply all the constants together. Do you agree with that? And the product of all those constants is going to be a constant, right? And that product will be whatever the constant term is in our original polynomial, right? That's the only constant on the left, and the only constant on the right will be the product of all those little numbers there. Do you agree with that? Can you see that? At the same time, at some point we'll multiply all those front numbers, bx, b1x, b2x, b3x, b4x, and that will be our leading term at some point. The products of all first terms will give me the highest exponent. It will equal my leading term. Okay? Do you agree with that? Therefore, I can say that any of those b's, so any b sub I is a factor of a sub n. Each of those b's has to divide a sub n if the product of them equals a sub n, right? And at the same time, any of those c's, any of the c sub i's, is a factor of the constant term, right? What do you think? Well, it just is, you know, because there's just some number there, okay? Now, if we focus on the cases where b sub i's and c sub i's are integers, we just look at those cases, then, you know, if you set one of those factors to 0, and again, don't write this down. I'm just talking crazy here, and I warned you that I'll be talking crazy a lot through this section. If you set this factor to 0, then x equals c sub I over b sub I. That will be one of the zeros, where c, as we just agreed, is a factor of the constant term and b is a factor of the leading coefficient. Do you agree with that? Because we just discussed that if you multiply all the c's, you get the constant term. If you multiply all the b's, you get the leading coefficient. So then if you start dividing one by the other, when you solve for the zeros, you're going to get the numerator as a factor of the constant term, and the denominator is the factor of the leading coefficient. So this will answer that big question that we had earlier today. On this example, where I give you one of the possible zeros and we know the place to start. Whatever I just talked about, it will allow us to reduce the number of potential zeros, because what this thing tells me is that if my polynomial has a rational zero, then it has to be in the form of a factor of the constant term divided by the factor of the leading coefficient. It has to be, it won't have any other rational zero. So this gives us a theorem that's called the rational zero theorem. And this is a big deal. And you really need to know the theorem. You don't need to know the logic behind it, but it's kind of like where it comes from. And, well, your book states it. Let's see. Where is the statement? Okay, so rational zero theorem. So again, looking at a polynomial function, so let p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to the constant. Then if p of x has a rational zero, and let's call it p over q, that's how your book calls it, so just a fraction, you know, p over q, then p is a factor of a sub 0, so the numerator comes from the constant term. So the numerator is a factor of the constant term. And q is a factor of a sub n, the leading coefficient. Where p and q, those are integers. Okay, so we're looking at just rational zeros. So this will allow us to kind of reduce our options for rational zeros. That's all it does, really. So earlier when I asked you if you're just going to guess, you told me you have infinitely many options. Well, now instead of having infinitely many options, you might have, I don't know, 12 options. Still large, but that's a huge improvement, right? Versus just completely shooting in the dark or down to something a little more reasonable. So let's say if a of 0 equals 8, okay? And I was actually going to do an example to explain it in great detail, but what are the factors of 8? 2, 4, 1, and 8, and plus or minus. We're going to consider that. So which integers divide 8? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So those would be the factors of 8. So let me give you just an example. I'm going to give you a polynomial equals 3x to the 4th minus 11x cubed plus 10x minus 4. So I'm going to ask you this question. List all possible rational zeros of this polynomial. So that means all factors of the constant term divided by all factors of the leading coefficient. So this is how we're going to start. I'm just going to say, all right, so possibilities, is that how your book puts it? Yeah, possibilities of P divided by possibilities of Q. So what are the factors of -4? What integers divide -4? We'll have plus or minus 1, plus or minus 2, and plus or minus 4. Is the constant, right? So the numerator is the constant, denominator is the leading coefficient, which is 3. So what divides 3? Yeah, 1 and 3, so plus or minus 1 and plus or minus 3. So then here are my options for P over Q's. Let's actually do the division. If I divide 1 by 1, I'll just get 1, right? If I divide everything by 1, I'll get the same numbers back. So it's plus or minus 1, plus or minus 2, plus or minus 4. So this potentially could be my rational zeros. My rational zeros will be in that list. But also, I haven't finished yet. And when I divide by 3, you get plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. So this right there is the list of all possible rational zeros, which is actually 12, right? There are a total of 12 numbers. Okay? So if our polynomial has rational zeros, it's going to be in that list. Okay? So now if I ask you, here's the second question. Is x equals 5 a zero of this polynomial? You're going to say, no, it's not on the list. It's not part of our possible rational zero list. So the answer is no. X equals 5 is not on the list. So right away we know 5 won't work. We don't have to do the synthetic division. We know 5 doesn't work. What if I ask you, is x equals 2 a zero of P of x? Possible. We don't know, but it could be because it's on the list. So maybe, so let's test. 2 is on the list, so we're going to run 2 through our polynomial. That's where we have to do the synthetic division. So what are coefficients? 3, -11, 0, 10, -4, right? 3, -11, 0, 10, -4. So if we run 2 through this, 3 comes down, 2 times 3 is 6. Add the two numbers, we get -5. Multiply, you get -10. Add again, you get -10. Multiply, you get -20. Yeah, so you get -10 again, -20, -24. So no, it's not a zero. So you see, just because it's on the list, it doesn't make it a zero. It makes it one of the possibilities. So now x equals 2 is not one of the zeros. How's that? Does that make sense? Now, if you're just given this question, So it still kind of sucks, right? We just tested one of the zeros, didn't work. We still have 11 possibilities, right? Well, or yeah, if you're really unlucky today, that means you miss on the first 9, and then all of a sudden you start hitting, or maybe, you know, not 9, maybe 8. But I mean, if I just tell you, start testing, each one of you can grab a different number, and one gets lucky, the other one doesn't. So in this case, we can actually do something like this. We can grab this function, okay? We can use our whatever graphing device or computer or graphing calculator to grab this thing, which is what? 3x to the power 3, 4, x to the third plus 10 times x minus 4. All right, I don't know what just happened. Oh, it gives me the x squared again. Go away. All right. Well, I kind of look at the x-intercept, right? Because that kind of tell me potentially what the 0 is, and that looks like -1. Well, it's not really a half, so this is where we have to be careful. Maybe 3/4. See, here's the thing. This could be, when you look at those intercepts that are not pretty, like not the integers, those could be irrational zeros. They're not on our list. Our list only produces rational zeros. But we for sure see how -1 looks like -1, right? So let's test -1, see if that works. So you can do that. You can do that little. Yeah, so at least it will give you an idea which x-intercepts are close to 0. So let's test -1. So if we run -1 through this thing, so 3 comes down, -3, -14, is it? Then 14, 14, -14, -4, 4, 0. So yeah, that one works. Okay. All right, so -1, x equals -1 is one of the zeros. But our quotient is still a cubic, and the cubics are hard to solve, right? So we got one of the zeros. We still potentially can have 3 more. Remember, the 4th degree polynomial will have 4 zeros. Well, with multiplicities or whatever. So by going back to our graph, what else do you think might work? I mean, you see, we have this 0 all the way to the right, which is around 3.5, right? It's a little less than 3.5, but do we have anything on our list of rational zeros that's kind of 3.5? 4/3 is just 1 1/3, right? So we don't have anything around 3.5, so that means that 0 is one of the irrationals. We'll have to do some extra work to find that one. But we have the 2/3 as one of the zeros, and it does, yeah, and that thing between 0 and 1 looks like kind of 2/3, right? So let's try that. Actually, it looks like it has a multiplicity too, but we'll worry about that a little later. But looks like 2/3, so let's try that one. I'm not saying it is 2/3. It could be something weird, but at least it looks close. So if we run 2/3, but remember, run your future test through the quotient. The second that you get the 0 for the remainder, continue your synthetic divisions through quotients. Because then if 3/4 works, this cubic will turn into a quadratic, and we can always solve quadratics. Okay? So let's try that one. So what did we say? 2/3? Run 2/3 through 3, negative 14, 14, negative 4. So we have to do some, have to be multiplying fractions or whatnot. Okay? So 3 comes down. What is 2/3 times 3? 2. Negative 14 plus 2 is negative 12. So it's still easy to multiply by 2/3. What's negative 12 times 2/3? Negative 8. Because you just divide by 3 and then you multiply by 2. So what is the sum? What is the sum here? 6. 2/3 times 6 is 4. Well, 2/3 means divide by 3 and multiply by 2. That's what 2/3 is. So just dividing by 3, multiplying by 2. So yeah. No. 12 divided by 3 is 4 times 2 is 8. Right? So that's what we got. We got negative 8. Yeah.
Oh, yeah, sorry.
Well, actually, I wouldn't, because every time I get down to this, it's a quadratic, and I can always solve a quadratic, right? I can always solve that. So we got x equals 2/3 is a 0. And again, I don't know whether, if I go back to this graph, I don't know whether it's a multiplicity too. Maybe it crosses the graph ever so slightly and turns around. I mean, I don't see that, right? If I zoom in closer, where's my zoom in option here? Is there one? I don't know. I mean, if I do the window between 2/3, how about I'll do between 0.5 and 0.75. I don't know, maybe it does bounce, but I don't know. That's all I'm saying, right? So again, we cannot really go off of the graph, but the graph kind of gives us a hint where might be a good idea to play with. But anyways, whatever this thing is, that's a quadratic. So I can take that and set it equal to 0 to find the rest. So 3x squared minus 12x plus 6 equals 0, right? I can divide everything by 3 to make my life a little easier. So this is x squared minus 4x plus 2 equals 0. Right? Did I divide it correctly? If I divide everything by 3? So then use the quadratic formula. So that's 4 plus or minus the square root of 16b squared minus 4 times a times c over 2a. Okay? Actually, I don't think 2/3 will appear there again. It looked like it bounced off, but it didn't. Because if I keep solving, this is 4 plus or minus the square root of 8, right? 16 minus 8 over 2. I can simplify the square root of 8, because 8 is 4 times 2, so it becomes 4 plus or minus 2 square roots of 2 over 2. So this is 2 plus or minus the square root of 2, right? So I don't get another 2/3, but 2 minus square root of 2, I bet it's really, really close to 2/3. Because look, if I plug that into a calculator, if I do 2 minus the square root of 2, yeah, so it's 2/3 is 0.66. This is 0.59. So that's why it looks like it bounces off there, but it doesn't. I don't know why that opened up. All right, so these are our 4 zeros. Well, you take the square root of both, and square root of 4 is 2, and the square root of 2 is square root of 2, so that stays. So the zeros x equals -1, x equals 2/3, and x equals 2 plus or minus the square root of 2. So those will, okay, this graph is bad now, but those were those two other zeros. They're irrational. They're not on our list. Our list only produces possible rational zeros, okay? No, we got 4. We got 1, 2, 3, 4, right? Yeah, so, and we start with the 4th degree, so we're good. These are all possible zeros, okay? And if we wanted to, if the problem was to write down our polynomial as a factor, what was our polynomial originally? P of x. So our P of x equals x plus 1, x minus 2/3, x minus 2 minus the square root of 2, x minus 2 plus the square root of 2. So these would be all the linear factors of our polynomial x plus 1, x minus 2/3, x minus 2 plus the square root of 2, x minus 2 minus the square root of 2. So this is our polynomial in a very much factored form. And it's okay to have x minus 2/3 in there. We don't have to fix that. We know if we FOIL this out, we'll get our thing. Where is it? We'll get our original polynomial. If we FOIL that, we'll get that. Yeah. So this would be all the zeros. This would be our polynomial written as a product of linear factors. How's that? Yeah, it is long. Let's try another one. So, oh yeah, let me give you a little break. Let's take a little break and then we'll do another 45-minute problem. So on this last question, I actually have to be a little more careful. We found the zeros. This is all good, okay? But here, when I was solving for x, when I divide by both sides by 3, that's all legal. But it really means that 3 is also a factor, because this quotient, 3x squared minus 12x plus 6 is 3 times x squared minus 4x plus 2. So 3 is also a factor of our polynomial. So when I wrote this last statement, does not equal the original problem. I'm missing that 3 here. So it needs a multiple of 3. Okay? And if I multiply 3 through, let's say, this parenthesis, that's how we were doing it earlier, getting rid of the fractions. I'll get x plus 1, 3x minus 2, x minus 2 plus square root of 2, x minus 2 minus square root of 2. So this identically equal our original problem. So that this way you get 3x to the 4th as your leading term. Otherwise, you just get x to the 4th. But you still get the same zeros. See, that multiple doesn't affect the zeros. Question?
Why don't you just distribute it to
Oh, well, I could distribute through anyone. It's just nice to go through the one that has a fraction because it kills the fraction. Okay? So it does have that extra 3 in there because that was part of the problem, right? It's part of the quotient. When you solve the equations, it doesn't matter that constant, but as far as the original function goes, it does. So let me do another one where same thing will come up. So here's a polynomial f of x equals 2x to the power 5 minus x to the power 4 minus 4x cubed plus 2x squared minus 30x plus 15. Okay, so I want to start just by listing all possible rational zeros. So we're going to list all possible rational zeros. So the options for p, for the numerator, would be all the factors of the constant. So 15, it can be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So these are all possible factors of that constant term, while the possibilities for q, the denominator, will be all the possible factors of leading coefficient, which is 2, so plus or minus 1, plus or minus 2. So now when you actually start dividing, you can get plus or minus 1. When you divide by 1, plus or minus 3, plus or minus 5, plus or minus 15. And when you divide by 2, you can get plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, plus or minus 15/2. So this right there is the list of all possible rational zeros, which, what, 16 option? That's quite large. Okay. Is that okay how we got that list? So you get the all, you 15 over 2, so all the possible factors. So, well, it would be hard for me to just graph it. But this is the whole point of, let me just reload this thing. Oops. I'll just plug it in. So if I type that in, 2 times x to the power of 5 minus x to the power of 4 minus 4x to the power 3 plus 2 times x to the power 2 minus 30x plus 15. Okay, that looks okay. Again, I don't want this thing. Well, I don't think it goes through 0, but it's pretty clear that it goes through a half, right? I mean, this one between 2 and 2.5, I don't know what that one is. But again, I don't think it's exactly in the middle, but that one looks like 1/2 should work, right? And 1/2 is on our list, so I would start with 1/2, okay? Well, 1/2 is right here, it's on the list, so here's 1/2. So it looks like from the graph, a 1/2 would be a good place to start. So let's try 1/2. So 1/2 goes on the outside, and the coefficients are 2, -1, -4, 2, 30, -30, and 15. So these are our coefficients. So 2 comes down, 1/2 times 2 is 1. -1 plus 1 is 0. 0 times 1/2 is 0. Negative 4 comes down. Negative 4 times 1/2 is negative 2. The sum of 2, negative 2 is again 0. Is that right? 1/2 times 0 is 0, so negative 30 comes down. Negative 30 times 1/2 is negative 15. So we do get 0 in the end. So yes, 1/2 works. Right? Let's see what we have left. This quotient right there. You see it has few zeros in there? Because as of right now, our polynomial is x minus 1/2. So, 1/2 is one of the zeros, so x minus 1/2 is a factor. And then times all that, which is, this is 2x to the power 4 minus 4x squared minus 30. Is that right? Doesn't have a cubic, doesn't have the first power. Again, these are my coefficients, and the way you read that, this is the constant, this is the x, this is the x squared, this is the cube, and this is the fourth. So you really read from right to left. So these are the constants, this is the x, this is the x squared, this is the x cubed, and then this is the x to the fourth. You just count backwards. Now, out of that fourth degree, I can pull out a 2, right? We can pull out a 2 out of that. And that leaves us with x to the fourth minus 2 x squared minus 15. Is that okay? Now, if I just focus on this one, if I just focus on this fourth degree polynomial, it has that quadratic pattern. It does look like a quadratic as far as the, it has x squared and x to the fourth. Just like the quadratic has just x and x squared. I can factor this just like I factor quadratics. I need two numbers that multiply to negative 15 and add to negative 2. Can you think of two numbers that multiply to negative 15 and add to negative 2? So negative 5 and positive 3. So that can be factored by some old school factoring into x squared minus 5 and x squared plus 3. Do you agree with that? Well, now, these are both quadratics. If I set them equal to 0, x squared minus 5 equals 0, and x squared plus 3 equals 0, I'll get x squared equals 5, which means x equals plus or minus the square root of 5. So these are the two more zeros. Those are irrational zeros. They're not on our list. The other one, x squared equals negative 3, so x equals plus or minus square root of negative 3, which means plus or minus I square root of 3. Those are imaginary zeros. They're still not on our list. So our list only had one zero that actually worked. But these are all 5 zeros now, right? We got 1/2, and we got plus or minus root 5, plus or minus I root 5. So if I go back to the graph, those two things that look like negative, like 2 1/4 and negative 2 1/4, those are your square roots of 5s. That's your plus or minus square root of 5. And you don't see the I square root of 3 on the graph. It doesn't show up there. Well, right, and that's what we got, right? Those are exact opposites, so they're mirror images of each other, right? If I plug in square root of 5 into the calculator, you see it looks 2.23, and you were guessing 2 1/4, but so these are all my 5 zeros, right? We started with the 5th degree, and we got x equals 1/2. So here are the zeros. 1/2 plus or minus root 5 plus or minus I square root of 3. So these are the zeros. Now, if the problem was also asking us to write it in linear factors, so what are my factors? We have x minus 1/2. That was one of the factors. We had the 2, so let's not forget about the 2. 2 was one of the factors. And then we have x minus square root of 5, x plus square root of 5, and then we have x minus I square root of 3, x plus I square root of 3. So these are my 5 linear factors. And as before, I can throw the 2 inside the first parenthesis to make it 2x minus 1, so I don't have a fraction in there. So it'll still be the same. So, or my polynomial is 2x minus 1, x minus root 5, x plus root 5, x minus I square root of 3, x plus I square root of 3. Yes? Uh-huh. Right. Well, that's why we looked at the graph first.
So like there's
No, could be all 5 on that list. All right? But the problem is where to start. And this is where we use the graph. Yeah, so the other 4 were 2 irrational, 2 imaginary, so they're not rational. The list only gives us possible rational zeros. So this is why we looked at the graph first. And the graph suggested us what looks like 1/2 is going to work. And that's why we started with 1/2. It could be more. Yeah. And then just going forward, just like in the previous example, we had 2 numbers work, right? -1 and 2/3 worked out of the list, and the rest were irrational. Okay, so it could be all zeros could be on the list, but the reason why we do the division so we can get to a point where we find the non-rational zeros, the square roots and the imaginaries. Yeah, it will show up through the synthetic. Yeah. 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 Yeah, you're probably not gonna. Yeah, then you're really in trouble. Yeah. Then you do that, the intermediate value theorem, and you start doing it numerically. Um, I know I shouldn't be doing that. I have a problem in mind, but I don't see it. Something like that. Let's try this one. I'm not sure whether that's going to work, but here's a nice little pattern that I want to address. So let's say we have 2x to the 4th minus 3x cubed minus x plus 8. I just want us, again, first to list possible rational zeros. So again, these are your p's over q's. So p's would be the factors of the constant. Q's would be the factors of the leading. So constant term is 8. So we'll always get plus or minus 1. Then we can get plus or minus 2, plus or minus 4, and plus or minus 8. Right? These are all possible factors of the constant term. Now the denominator would be the possible factors of the leading coefficient. which is 2, so we get plus or minus 1 and plus or minus 2. Is that right? Well, now, when we actually start dividing, and we have to be a little careful because we don't want to list same possibilities more than once. That would be silly. But if I divide everything by 1, 1 by 1 is plus or minus 1, 2 by 1 is plus or minus 2, 4 by 1 is plus or minus 4, plus or minus 8. So you get the numerator. Now when we start dividing by 2, 1 by 2 is plus or minus 1/2, right? When you start dividing by 2, yeah.
So show me how you get the list here with Q, like plus minus numbers,
I just did. I'm not sure what you're asking then. Because again, the P is that. So everything that divides 8. So that's what I'm putting there. So 1, 2, 4, 8 with the plus or minus because it both works. And the Q, that will be, Q comes from here. Okay? No, it's all right. But is it okay when you divide everything by 1, you just get the same thing back. And now dividing by 2, you have to be a little careful. 1 by 2 is 1/2. But what is 2 by 2? 1. And we already listed 1. So I don't want to list it again. Then what is 4 by 2? 2. And we already listed that. And 8 divided by 2 is 4. So we already listed that. So there's no reason to overlist that. So that's it. These are the all possible rational zeros. So this is why I wanted to bring this example, just to show you that sometimes you get same results, so no reason to list them again. So if you already got plus minus 2, you don't have to do it again. Is that clear? Now for the rest of the problem, there could be one of those examples that nothing works. Okay, so I found this problem in your book, and the book just said list the zeros, which is always alarming. It didn't say to do anything else. It might not work, but let's make an attempt. Okay? No? So here's one thing I want to share with you. There's a really quick way to see whether 1 works. Okay? We don't have to do synthetic division to check whether 1 works. If the sum of all coefficients equals 0, then 1 will work, right? Because if you plug in 1 for x, it just kills all the x's, and you're left with the coefficients. So is the sum of all coefficients equal 0? No, so we know 1 is not going to work. Okay? There's also a way to test -1. It's a little trickier. Yeah?
So synthetic division is basically the same thing as just plugging it in. If you have easy numbers.
Right, it's plugging in, but again, plugging in 1/2, you start, when you plug in fractions, you have to raise it to the power 4, and that's hard. But synthetic division is always easy, regardless of how big the problem is. To test -1, you just have to change the signs of all the odd exponents. So -3 becomes positive, -1 becomes positive, but the sum is still not 0. So neither 1 nor -1 are going to work in this case. But anyway, so when in doubt, let's start graphing. So let's use this thing. So what's our polynomial? Have to tell me, I forgot already. 2 times x to the power 4 minus 3x cubed. X cubed minus x plus 8. What, it didn't even graph it? So, yeah, so yeah, see what that tells us, it has no real zeros, period. Okay, so we cannot, there's nothing else we can do with this one. Yeah. Well, just keep zooming out, I mean, so that's about it, you see. It has no real zeros at all, right? Yeah, so it doesn't cross the x-axis, right? At all. So remember how we said if it crosses the x-axis, then it's a 0 and it's a factor. So that means all the zeros are imaginary. If I actually solve for x, if I am successful, all my zeros will come up with i's in them. Okay? And it's a 4th degree, right? It's a 4th degree polynomial, so it means I'm going to have 2 pairs of complex conjugates. Okay? If you have an odd degree polynomial, it will always cross the x-axis at some point. So you're guaranteed to have at least one real 0. But even degree, just you have this parabola-looking thing just kind of sits on the top, never crosses the x-axis. So there's nothing else we can do with that. I mean, at this point in this course, we just stuck with that one. Well, no real zeros. So this is why this problem was only was asking you to do the list, because there's nothing else you can do at this point. So that's why I said, it's a little alarming. But the reason why I wanted to do that is to show, when you start getting the duplicate zeros, just don't list them again. So how is that? Is this fun? Want to try one more? What was that? Let's do one more and then we'll stop. I'm not going to start section 4.5. There's no reason to do that. So f of x equals, let's try this one, x to the 5th minus 5x to the 4th plus 5x cubed plus 15x squared minus 36x plus 20. So 5th degree. Yeah. So the exercise is asking us to find only the rational zeros. So maybe there is a problem finding all of them, but let's start with let's see what we can do with this one. But again, we should always start with the list of all possible rational zeros. Well, in this case, since your leading coefficient is just 1, so your possibilities will just be the factors of 20. Okay? There's, you're dividing by 1, it's plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20, over plus or minus 1. So your denominator doesn't even matter in this case. Do you agree with that? So your possible rational zeros are just those. So these are the possibilities. So I see some of you already graphed it. No? Yeah, so what do you think? What is a reasonable place? Well, remember how I told you if the sum of all coefficients equals 0, then 1 most likely, it will work. What is the sum of coefficients there? 0, right? If I add them, you have 20 minus 36, so that's negative 16. 5 and 5 cancel, and the other two give you positive 16. So 1 will work. So that's what I'm going to start with. I'm going to test 1. And then we'll drop 5th degree to 4th degree. Then we're going to look at the 4th degree and see whether that one is friendly. So let's test x equals 1 first. You should always, and again, the reason why we do the test, even if we're certain that 1 is going to work, and we are in this case, but you have to do the test to reduce your polynomial. That's the biggest benefit of that. So when you run 1 through this thing, what are the coefficients? 1, negative 5, 5, 15, negative 36, 20. So running synthetic division reduces the degree of our polynomial. So 1, 1 is 1, negative 4, 1. Is that right? So 1 again, 16, negative 20, negative 20, 0. Right? So 1 works. So at this point, our polynomial is x minus 1, and this is a 4th degree, so this is x to the 4th minus 4x cubed plus x squared plus 16 minus 20. right? I'm missing an x here, 16x. Okay, so now what do we have? See, we have to see is anything going to divide that other polynomial. And this is, again, you have to rely on the graph, because there's nothing we can do with that with our old algebraic tools. Like, it's hard for us to factor. So I'm just going to sketch the graph of that one. I'm going to sketch the graph of my quotient. So x to the fourth. I don't know. I'm tired of typing all the. Okay, it doesn't like it wants to do the times. Plus x squared plus 16x minus 20. No, I'm down with that one. I just want to look at the quotient, what the quotient looks like. So yeah, nothing good, right? If I zoom in, oh, so it does look like a 2 and a negative 2, does it? So let's run those. Let's run 2 through this thing, so we can find the rest. So if I run 2, so I need to take this quotient, and I'm going to run 2 through the quotient. 1, negative 4, 1, 16, negative 20. So I'm going to run 2 through this. 2 is on the list. So 1, 2, negative 2, negative 4. Am I doing this right? Negative 3, negative 6, 10, 20, 0. So 2 worked, right? But also looked like negative 2 is going to work. So I'm going to write negative 2 through this quotient. 1, negative 2, negative 4, right? 8, 5, negative 10, 0. So that's also going to work. Is that okay? So what do we get? So x equals 1, x equals plus or minus 2. We got that so far. And we're down to this quadratic, x squared minus 4x plus 5. Do you agree with that? But we got our rational zeros. These are all rational zeros. Because that thing will produce 2 irrational, maybe 2 imaginary, I don't know. But the zeros of that quadratic are going to be non-rational. If I wanted to find the rest of them, I would just use the quadratic formula, right? And if that was the question, if I set it equal to 0, and I use the quadratic formula on that, so it's 4 plus or minus the square root. 4 squared is 16 minus 4ac over 2a. So yeah, it produces imaginary negative 4 over 2. So this is 4 plus or minus 2i over 2. So these are 2 more. Okay? So all the zeros are 1 plus or minus 2 and 2 plus or minus I. Okay, so here's the case where 3 of the zeros were on the list and the other 2 weren't. Okay? How's this? Does this make sense? How we do that? All right, good. So this is your section 4.4. Now you can finish the homework and the quiz Friday. Yeah. And then we'll start 4.5. Now, that one is already pushed for Wednesday, the other one. And we'll see how we do on that. So that's what this is the announcement I made at the beginning of the class. If you came in late about when the quizzes are due right now. If you came in a little late, you might have missed that. Right, no quiz because we just finished whatever we need for the quiz, but you should be able to do at least most of the homework by the quiz, so. All right, good.